Have you ever been trapped in a revolving door, pushing and pushing but never actually getting into the building? That endless, frustrating loop is a perfect physical copy of what happens inside a computer when it crashes. This photograph shows an early computer reading a spool of paper tape. To understand why computers get stuck, look at how it pulls data. It reads one punched hole, follows the instruction, and moves to the next hole in a straight line. Here is a portrait of mathematician Alan Turing. In the 1930s, he proved that this straight-line reading method creates a permanent blind spot. If a set of instructions contains a trap that tells the computer to loop back on itself entirely, the machine cannot look ahead to see it. Computer scientists call this the halting problem. This image displays rows of vacuum tubes inside an early computer room. Engineers physically wired that step-by-step chronological logic straight into the hardware of these massive machines. Because of that hardware, a standard computer only finds out what an instruction does by actually performing it. If there is a contradiction hidden deep in the code, the system steps right into the trap and attempts to run a calculation that has no end, which freezes the whole system. The machine is trapped in the present moment. It has no way to predict an endless cycle without getting caught in it first. To bypass that blind spot, we need the computer to see itself from the outside. This is called self-state registration. Self-state means the computer takes a snapshot of its internal settings, and registration means it pins that snapshot onto a master map, like a GPS coordinate. Instead of walking step by step through the maze, the system flies high above it. It stops experiencing a chronological sequence of events and starts looking down at a complete map of every possible turn. We see this transition as a single line of code expands outward, translating chronological instructions into a wide, physical state matrix. Here, code is a set of directions. Every possible decision has a specific home on this grid, lighting up simultaneously. Because every if and then statement now has a permanent physical location on the map, the system doesn't wait for clocks to see where the path leads. It can survey the entire lifespan of the program as a single static shape. To check if those paths are safe, the system duplicates the map into two parallel layers. The top layer, the primary core, represents instructions as written. Every yes becomes a physical peak. The bottom layer is a mirror core. It's an inverted simulation where every yes is turned into a valley. This creates a mathematical mask, where the bottom layer is the perfect opposite of the top. Instead of running the program to see if it works, the system simply presses these two opposing physical maps together. If the code is logical, the peaks and valleys fit together perfectly. The yes from one side and the no from the other cancel out, leaving a perfectly flat surface. This flat result proves the math adds up to 0, meaning the program will eventually finish its task and halt safely. This physical interlocking acts as an instant structural proof. The system knows the program is safe because it fits together like a perfectly solved puzzle before a single line of code actually executes. So what happens to this map when the code contains a loop that never ends? Remember, in a loop, the computer is told to do the same thing forever. Mathematically, this means the code never resolves to 0. There is always a leftover piece of data that won't go away. When the two layers press together now, that leftover data has nowhere to go. Because a loop is a logical contradiction, the peaks and valleys can't cancel each other out. This mathematical remainder is forced out of the matrix, appearing as a jagged, physical bulge on the map. The AI doesn't need to trace the loop to find it. It just sweeps a scanning plane across the surface. When it hits that protruding spike, it has instantly located the crash before it even happens. The system simply isolates that specific coordinate on the map and deletes the faulty instructions. It clears the danger without ever having taken a single step into the trap. Self-state registration defeats the halting problem by transforming logical time into a physical territory. By checking the shape of the code rather than walking the path, the system can safely navigate around computational landmines without ever having to step on them.